In this video, we'll explore one of the most provocative ideas in contemporary theoretical physics, the possibility of retrocausality or reverse causality, where future events affect the present. This concept challenges the traditional view of causality, which assumes that causes precede their effects in a linear, forward progression of time. We'll ask whether our current state is simply the result of past events, or whether future events also affect our current state. The idea of retrocausality, which suggests that cause-effect relationships can also flow from the future to the past, pushes the boundaries of classical mechanics, where causality is one way, past to future, and instead proposes a two-way causality that could allow the future to shape the past. This theoretical framework is particularly important in the context of quantum mechanics, a field that currently challenges many classical intuitions. Quantum theory is fundamentally probabilistic, based on the uncertainty principles inherent in properties of particles such as position and momentum. Quantum mechanics provides a probability wave rather than definite conclusions, gives us a superposition of all the possible states a particle can occupy. When a measurement is made, this superposition collapses into a single result, but up until that moment, all the possibilities coexist. This randomness, or quantum uncertainty, raises questions about the nature of reality and the limits of classical causality. Let's present a compelling scenario using the thought experiment of radioactive decay, which is an inherently probabilistic process. Even if two identical atoms are in identical states, the exact moment of decay for each cannot be predicted with certainty. It is completely random and governed by a probability distribution. Physicists Jeff Tollaksen and Yakir Aharonov designed an experiment to test the effects of future measurements on current conditions, and they relied on the concept of weak measurement in their experiment. This is a technique that allows a quantum system to be observed without completely collapsing its wave function and aims to provide experimental evidence for retrocausality. The analogy of a boat on water is used to explain how both past and future events can affect the present. The waves represent quantum probability waves. If the future can affect the present, then the waves from both directions, past and future, can interfere, leading to a stronger, measurable effect than if only past events were considered. They outline how weak measurements are inherently imprecise, although they are less invasive and allow the superposition of states to remain intact. As a result, experimental data must be collected over many measurements to discern meaningful patterns. The main conclusion discussed is that these experiments do indeed show some amplification effects in the second measurement stage, suggesting an influence from the future. The necessity of collecting data from a large number of weak measurements introduces significant uncertainties and potential margins of error that preclude definitive claims about retrocausality. Although this line of research is interesting and opens up new avenues for research, it is not yet sufficient to overturn the classical view of causality or to fully integrate retrocausality into the framework of quantum mechanics. Retrocausality remains a speculative theory. The challenge lies in developing more precise experimental techniques that can confirm or refute the idea that the future can affect the past, potentially reshaping our understanding of time and causality in the quantum realm. This discussion reminds us that our understanding of reality in quantum physics is deeply mysterious and far from complete, and that much remains to be discovered in the interplay between time, causality, and quantum mechanics. In this context, we will also examine a deep aspect of quantum mechanics and its implications for our understanding of reality. Let us focus on the challenges that quantum theory poses to classical notions of realism and determinism, particularly through the study of the wave-particle duality of quantum objects such as photons. This duality lies at the heart of quantum mechanics. It is worth noting that John Wheeler, a well-known theoretical physicist, famously illustrated the strange nature of quantum phenomena with the metaphor of the Great Smoking Dragon. This dragon represents a photon traveling from its source to a detector. The beginning and end of the photon are sharp and well-defined, its tail and mouth. But the state of the photon between these points, the body of the dragon, is vague and hazy. This metaphor summarizes the quantum idea that a particle has no well-defined reality between its emission and detection, and is consistent with the philosophical stance known as anti-realism. Anti-realism in quantum mechanics holds that quantum objects do not have definite, intrinsic properties until they are observed. Wheeler extended this idea into an experimental challenge to realism, which holds that quantum objects, such as photons, always have definite properties regardless of observation. Wheeler's experiment was designed to corner realists, where they would be forced to accept the seemingly absurd idea that the future could affect the past, a scenario that challenges our traditional understanding of causality and time. This experiment became an influential argument for anti-realism, suggesting that we should abandon the idea that quantum objects have definite properties in the absence of measurement. However, this long-standing narrative was overturned when Rafael Chaves and his team at the International Institute of Physics in Brazil identified a gap in Wheeler's experiment. They showed that, under certain assumptions, it was possible to explain Wheeler's results using a classical model that allowed photons to have an internal structure. This classical interpretation showed that the dragon could have a well-defined body, but one that was hidden from the formalism of standard quantum mechanics. Chaves' work reopened the door to hidden variable theories, an alternative interpretation of quantum mechanics in which quantum objects are not fundamentally definite, but merely have definite properties that are hidden from us. This reignited the debate over realism in quantum mechanics. This discovery, remarkably, prompted an immediate experimental response. 3 independent research groups quickly ran modified versions of Wheeler's experiment to test the proposed gap, as suggested by Chaves' team. In quantum mechanics, entities such as photons can exhibit both particle-like and wave-like behavior, but crucially, they never exhibit both at the same time. Wheeler's experiment is a variation of the famous double-slit experiment, using a setup known as the Mach-Zehnder interferometer. In this experiment, a single photon is fired into a beam splitter that creates 2 possible paths for the photon to travel. If only one beam splitter is used, the photon will behave like a particle, following one path and arriving at one of the 2 detectors, D1 or D2, with equal probability. This behavior is consistent with the classical idea that particles have a specific trajectory. However, when a second beam splitter is inserted where the 2 paths intersect, the situation changes dramatically. In this case, the photon behaves like a wave, following both paths simultaneously. The 2 possible paths interact with each other, creating either constructive interference or destructive interference. This wave-like behavior means that the photon does not have a well-defined path until it is observed, further supporting the quantum concept of anti-realism. Experiments initiated by Chaves and colleagues tested whether these results could be reconciled with a classical, realist interpretation. The experiments provided further evidence that quantum objects do not conform to classical expectations of having intrinsic properties that are independent of observation. The results reinforce the view that quantum mechanics, with its probabilistic and imprecise nature, remains the most consistent framework for understanding the behavior of the smallest particles in our universe. Wheeler's delayed choice experiment is a conceptual experiment designed to investigate the fundamental nature of quantum objects, whether they behave like particles or waves by nature, and more importantly, whether these properties are determined before measurement or only by observation. What happens if we postpone the decision to add a second beam splitter until the last moment after we have decided whether a photon will behave like a particle or a wave? In the experiment, a photon first encounters a beam splitter that sends it down one of two paths, or both if it behaves like a wave. If a second beam splitter is added at the intersection of these paths, the photon exhibits wave-like behavior, interacts with itself, and always ends up at a particular detector. Without the second beam splitter, the photon behaves like a particle, traveling along a single path and arriving at one of two possible detectors. Wheeler suggested that the addition of the second beam splitter be delayed until after the photon has probably made its choice. The surprising result, confirmed by both theory and experiment, is that when the second beam splitter is added, the photon behaves like a wave, even at the last possible moment. This shows that the photon has somehow been on both paths simultaneously up to that point, challenging our classical intuitions about reality and causality. The delayed choice experiment seems to imply retrocausality. Future events, the addition of the second beam splitter, can affect past events, the photon's path choice. In classical physics, this is an absurd proposition, since it would mean that effects can precede causes, violating the standard causal order. One way to get around the idea of retrocausality is to adopt anti-realism, the interpretation most often associated with the Copenhagen interpretation of quantum mechanics. This view suggests that quantum objects, such as photons, do not have definite properties, such as being particles or waves, until they are observed. In this framework, the photon's behavior does not become retrocausal, since it does not have an intrinsic reality independent of measurement. Instead, the photon only becomes real when it is measured, meaning that there is no fixed state to retrieve, and therefore no need for retrocausality. Causal modeling and hidden variables. In the context of Wheeler's experiment, we will introduce an important development that challenges the anti-realist interpretation. Rafael Chavez and his colleagues applied causal modeling, a framework for describing and analyzing cause and effect relationships within an experiment. Causal modeling gained momentum through the work of Judea Pearl and others, who used it to explore complex systems, particularly those where direct causality is difficult to determine. In the context of Wheeler's experiment, causal modeling was used to explore whether it was possible to explain the behavior of a photon with a classical model that included hidden variables and unknown factors that determine the properties of the photon before it is measured. Hidden variable theories aim to preserve realism by assuming that quantum objects have definite properties, but that these properties are affected by variables not accounted for in standard quantum mechanics. Chavez and his team began by assuming that the photon has an internal state determined by a hidden variable after it passes through the first beam splitter. This hidden variable will affect the behavior of the photon depending on whether or not a second beam splitter is added. Importantly, causal modeling prohibits retrocausality and ensures that the experimenter's choice to add or remove the second beam splitter cannot affect the photon's internal state in the past. The team successfully demonstrated that it is possible to create a classical causal model using hidden variables that can replicate the results predicted by quantum mechanics, indicating a potential gap in the delayed choice experiment. This finding was unexpected and led to further experiments to test whether this gap could be closed. Chavez and his colleagues proposed a modified version of the Wheeler experiment, in which instead of adding or removing the second beam splitter, they introduced two phase shifts at different points in the experiment. These phase shifts change the relative paths of the photon, affecting whether it behaves like a particle or a wave. The critical difference between classical hidden variable models and quantum mechanics is how these phase shifts affect interference patterns. By calculating the expected results for different phase shift settings, Chavez's team created a formula that can distinguish between classical hidden variable explanations and quantum mechanical predictions. If the calculated value of this formula is 0, the results can be explained by a classical model. If it is greater than 0, it indicates that no classical explanation can explain the observed results. The results showed that the formula consistently produced values greater than 0, confirming that classical causal models cannot explain the experimental results. This effectively closed the gap and strengthened the quantum mechanical explanation. The importance of these experiments lies in the fact that they reaffirm quantum mechanics' strange but accurate description of reality. Despite the possibility that a classical, realist interpretation could explain the delayed choice experiment, the experimental results have shown that quantum mechanics is still the simplest and most accurate model for describing the behavior of quantum objects. Closing this gap not only supports the quantum mechanical view, but also highlights the robustness of quantum theory against alternative explanations that attempt to preserve classical intuitions about reality. Xavi's work, which includes a new inequality that classical models fail to satisfy, provides important evidence against classical interpretations of quantum phenomena, especially in the context of Wheeler's delayed choice experiment. Xavi's formula assumes that the hidden variable used in the classical causal model can take only one of two possible values and represent one bit of information. This assumption is consistent with the nature of the quantum system in question, where the photon also effectively encodes one bit of information following one path or another in the interferometer. Xavi's argues that it is natural to restrict the hidden variable model to the same dimensionality because it allows a fair comparison between the classical and quantum models. However, this assumption is not without its limitations. If the hidden variable is allowed to carry more information, the classical causal model can regain its ability to explain the statistical results observed in experiments, potentially regaining some of the explanatory power that classical mechanics has lost in the face of quantum phenomena. The durability of de Broglie-Bohm theory. Despite the success of Xavi's work in challenging certain classical models, these findings do not invalidate all hidden variable theories. De Broglie-Bohm's theory, a deterministic interpretation of quantum mechanics, has not been affected by these experiments. This theory assumes that particles always have definite locations that behave like hidden variables and are guided by a pilot wave. In this view, both wave and particle coexist as real entities. As the wave passes through both paths of the interferometer, the particle follows one path or the other depending on the wave's guidance. The presence or absence of the second beam splitter in Wheeler's experiment affects the wave, which in turn directs the particle to a particular detector. Most importantly, the de Broglie-Bohm theory reproduces all the results of standard quantum mechanics while maintaining a realistic and deterministic framework. Theoretical physicist Howard Wiseman compares this to the Copenhagen interpretation, which is often associated with anti-realism. In the Copenhagen view, quantum objects do not have well-defined properties until they are observed. Therefore, there is no need to invoke retrocausality, since nothing can be said about the state of the photon before the measurement. In contrast, in the de Broglie-Bohm interpretation, reality exists independently of observation without the need for backward causality because there is a simple causal explanation of events unfolding forward in time. While recent experiments provide compelling evidence against certain classical models, Kaiser raises an important concern about the source of the randomness used in these experiments. In the experiments, the decision to add or remove the second beam splitter or to adjust the phase shifts was made using a quantum random number generator. However, since the experiment itself was a test of quantum mechanics, using quantum-generated randomness introduces a potential circularity. Essentially, quantum mechanics is used to test quantum mechanics. To address this, Kaiser and his colleagues proposed an alternative approach to generating randomness that is completely independent of quantum mechanics. They developed a method to generate random bits using photons from distant quasars more than halfway across the universe. These photons, collected by a telescope at the Table Mountain Observatory in California, are used to determine the experimental settings. By relying on cosmic sources of randomness, the researchers aim to eliminate any potential bias introduced by using quantum-generated randomness. For now, the results from Chavs's work and subsequent experiments have significantly advanced our understanding of quantum mechanics, but they have also highlighted persistent difficulties in interpreting quantum phenomena. While some hidden variable theories, especially those with limited information capacity, have been eliminated, others, such as de Broglie-Bohm's theory, remain viable. This ongoing debate reflects deep and unresolved tensions between classical realism and quantum mechanics. Wheeler's Great Smoking Dragon metaphor remains relevant. Chavs's work briefly brought the dragon's body, the true nature of quantum reality, into sharper focus, suggesting that we may be closer to understanding the mechanisms underlying quantum phenomena. But as the limitations of classical models become apparent and the complexity of quantum reality reasserts itself, the dragon has once again become smoky and vague. The dragon's body, representing the uncertain and counterintuitive nature of quantum mechanics, still eludes precise characterization, ensuring that the mysteries of the quantum world remain active and fertile ground for future research. Thanks for listening, and take care.